Prep grade 12 physics, looking at pulleys. In a pulley system, you've got two anythings, masses, and they're connected around a pulley, and so there's a change of direction. The beauty with pulleys is that we treat it as a one-dimensional problem. You got a system that's free to move, even though they're not, this is moving horizontally and this is moving down. We still treat it as a one-dimensional problem. It's just that because they're going to share an acceleration, right? And usually you're looking for the tension in this connecting string, and you have to assume the tension's constant throughout the whole string. So this is connected right around the pulley. You assume it's constant. And almost every problem that we do involves finding the tension and the acceleration. So the strategy to solving them is first to figure out what direction you think it's going to move and call that positive. In this case, if this thing's going to move at all, it's only going to move down. There's no reason, unless there's a force we're unaware of, that this would move that way, right? Assuming there's no friction. If there's friction, M2 might not be enough to pull M1. But if this was a frictionless system, imagine it's on a little ice rink or something, then you can be sure that it would move in this direction. So we'll call that our positive direction. So you choose where you think it's going to go, call that positive. And then the strategy is, take this mass, do a free body diagram on it, and come up with an equation based on your free body diagram for mass times acceleration, it was forward pulling force minus backward forces, downward force minus upward forces. And then you do the same thing over here. And the idea is that when you do it here, you end up with two unknowns. You don't know the acceleration, and you don't know the tension on this rope, right? And the tension is what's holding this mass back. Well, if you look over here, same thing. This one, you end up with a free body diagram where you don't know the acceleration and you don't know the tension, but the acceleration is the same for both, and the tension is the same for both. Therefore, you end up with two equations, two unknowns. And that's solving pulley problems, and we're going to do a couple. I have 3 different examples that you could see. So in this first one, I've got very similar to what I just showed you. You got a mass here and a mass here. Okay. What do we know? We know that I'm calling this one mass 1 and this one mass 2. We're going to have to make an assumption that there's no friction in this system. We always assume there's no friction on the pulley. But it doesn't say anything. Oh yeah, frictionless surface. So we know there's no friction right here. Okay, so this is a very straightforward example. So the steps that you follow is you draw a picture of the system. Imagine this was all you're given, right? You draw a picture of the system. You do a free body diagram on each mass, and then you solve for the tension acceleration. So looking at mass 1, this one here, I know that I've got tension that's going to pull it this way. We'll give Ft is the symbol for tension. There's nothing holding it back, right? And yes, there's normal and there's gravity, but since there's no friction, those things don't actually affect the question very much. So my net force statement is I've got my net force on this one is just equal to the tension, right? Well, the net force on this mass is its mass times acceleration, Newton's second law, and that's equal again to tension. So we know the mass is 32.5 kilograms, so this gives us an equation. 32.5a, where a is acceleration, is equal to the tension. The problem with this equation is I don't know a and I don't know tension, right? So this is, that's my first equation. I'm going to have to come up with a second equation, so I have 2 equations, 2 unknowns. So if I do a free body diagram on mass 2, here I've got gravity pulling it down and tension holding it up. So my net force is gravity minus tension, because I decided that this was down was my positive direction. So mass 2 times 9.8, or G, minus tension is equal to my net force. This time my net force on this is M2 times A equals gravity force minus tension. So 40A equals 40G minus Ft. So here's my second equation. Okay, so now I got 2 equations, 2 unknowns. What I chose to do is, if you remember substitution from grade 10 math, this one's all set up for me, right? So instead of writing Ft in equation 2, I'm going to sub in 32.5a. right? Because I know this is true. So now I say 40A, just taking it from here, 40A equals 40G minus, instead of FT, 32.5A. Okay? And solve for A. That's all I'm doing here. So just go through the steps, solve for A. So I have an acceleration of about 5.4 meters per second squared. Okay? I just leave the G in here, by the way, just for simplicity's sake. So now I know the A, acceleration of my system, and now I can find the FT because I have this equation, equation 1. So I substitute in, and I have a tension of 176 newtons. And, oh, sure, they're good answers. Tension's tough. We don't know what's a good answer for tension, but I do know that 5.4 makes sense because here's my guideline. If my acceleration ended up being greater than free fall, greater than 9.8, I probably screwed up, or Miss Stone gave you a bad question, okay? Because there's no way this is falling faster than free fall because it's got a tension holding it up. And why would it fall faster than free fall? So some number, less than 9.8 I know is a good number for this one. Okay, moving on to the next example. This one looks much more complicated, and it really is. There's a few things going on in this question, just making it significantly more complicated. Significant enough that I'm actually going to leave it and put it in its own video. So I'm going to do the next two examples in their own video.